Page 45, talking about the concept of work. Definition: if a variable force F moves an object in a positive direction along the x-axis from a point, from point A to point B, then the work done on the object is given by that integral. We're going to focus specifically on springs, and that leads us to Hooke's law, which tells us that F is equal to kx. All right, since we're talking about a variable force, then we would define it as a function of x. Depending on where x is, the force would be different. All right. And that should kind of make sense when you're stretching a spring. The level of force needed to stretch it or compress it varies depending on where or how far out you are in the stretching process. All right, so x is going to be the distance from equilibrium, and k is a spring constant, which we're generally going to have to solve for, unless they're nice and they just flat out give it to us. All right, so suppose it takes a force of 10 newtons in a negative direction to compress a spring 0.2 meters from the equilibrium position. All right, so I'm going to work off of the work formula, but I'm going to make a substitution, and that substitution is going to say that using Hooke's law in conjunction with this definition of variable force, the variable work formula, we would say k times x dx is the definition of work as it applies to a spring. All right, so we have 10 newtons in the negative direction. All right, so that's a measure of force, and what we need to do is make a determination of what that would translate to in terms of a spring constant. All right, so we know f of x is equal to kx. They're telling us that this is going to have a force of -10, essentially. All right. Now this is happening over an interval of 0.2 meters. And so multiply both sides by 5, and you get -50 is equal to k. Right, so that would be our spring constant. Now we could pop that into our work model. Knowing that the k value is -50, we're asked to find how much work is done to stretch the spring 0.5 meters from the equilibrium position. All right, so equilibrium position would be 0 meters. So we're looking at, I'm going to bring this in a schmidgy. Well, I want to make that look a little nicer. But from 0 to 0.5. Alright, so -25 x squared over the interval of 0 to 0.5. So -25 times 0.5 squared minus 0. So -25 times a quarter, -25 fourths. All right. So the negative part, well, that's related to the fact that the force was negative because it was in the negative direction, so it's implying direction. All right. Force is force. So whether it's positive or negative is only going to, really just capture the idea of direction. So that translates over into work as well. All right, now in terms of the units, well, in this process of integrating, we multiplied the units for force, which involved a distance, a linear distance in meters. So k was constant, so unitless meters. And then we had a change in meters. All right, so also meters. All right, so when we're coming up with our units, we want to take that into account as well. All right, so now you could also kind of look at it and say, well, the force part of it, the kx combined, was this concept of newtons. All right, so it was stated flat out. So you could actually kind of go after it and say, okay, well, if we know that this is a newton, which is also known as kilograms meters per second squared, then we can establish what the units of measure would be for our final answer, which would be kilograms meters per second squared multiplied by another set of meters. So kilograms meters squared over second squared. Or we could say that they're Newton meters. All right, newtons multiplied by meters, Newton meters. All right, so we can go that route as well. All right, so for number 6, suppose it takes a force of, I'm actually going to write out Newton meters because I never really liked that way of expressing it, because it looks like subtraction, and you know, it's not really that big of a deal. Most people look at it and say it's a dash, but you know, I'm using other operators, so kind of makes sense. So it's all right, Newton meters. All right, so kind of like the concept of a foot-pound. In fact, it is exactly that. All right, the foot being the linear distance, the pounds being the measure of force. All right, number 6, suppose it takes a force of 8 pounds to stretch a spring 6 inches from the equilibrium position. All right, so same setup. So force in terms of x is going to be equal to k multiplied by x. All right, it takes a force of 8 pounds. All right, now it didn't say which direction, so we're stretching it, so it's reasonable to assume that that's going to be a positive. I put the units there, but it certainly looks like I just wrote 816, so let me make that look a little nicer. All right, so k times the linear distance is 6 inches. All right, why am I putting the units here? Because I just want to kind of prove the point. All right, so k is going to be the spring constant of, well, 8 divided by 6 is going to be 4/3, 4 over 3 pounds per inch. All right, so we could say it's unitless, but we could also say that it has a measure associated with whatever the units were of the items or elements that make up the relation. All right, so for example, going back to the previous one, we had force in newtons. We had newtons equals k times meters, so this would be newtons over meters would be the quote-unquote units for the spring constant. But when you're talking about a constant, we tend not to really consider the units too much. But that being said, it also kind of fits sort of nicely when, you know, in solving for k, you know, if we have the kx dx, we know that we're looking at newtons per meter times meters times meters. One set of meters will cancel out, and that's another justification for your Newton meters. All right, so newtons times meters. All right, so probably maybe a little too lengthy of an explanation related to the units, but it's such an important idea to get a good understanding of what's going on behind the scenes that it's worth taking the time, in my opinion. How much work is done to stretch the spring 1 foot? All right, so inches to feet. So that's going to be 12 inches. So from equilibrium, so 0 to 12. And it did say from the equilibrium position. We don't want to confuse ourselves and think, okay, well, we've already stretched it 6 inches. Is it just the additional 6 inches that we're talking about? No, it's the whole shebang here. So K is 4/3 pounds per inch. And that's 12 inches. And the linear distance is going to be dx inches. All right, so just kind of keeping an eye on what the units would be. We have inches canceling out here. All right, so we're, if we're just kind of cleaning it up, and I'm not really going to integrate a constant without, like working with the variable first. I just wanted to show the units here. You see that we have pounds times inches. All right, so we're going to leave the x variable though. And so let me get the units out of here because it's going to be a hideous mess if I leave them in. So 4/3 is constant, x dx, integrate, so that we're talking 2/3 x squared over the interval of 0 to 12. You pop in the 12, it's going to give us something meaningful. Pop in the 0, you're going to get a 0, so we can disregard that. So 144 divided by 3, I don't remember that being, well, actually it would have to be, right? Because 12 is a factor of 144 and 3 is a factor of 12. So 48? Yeah, 48. I just double checked on my calculator. So times 2 is 96. I'm just going to double check that. Yep, 96. All right, so this is 96. I already forgot. Inch pounds. All right, and again, and I'll annotate it a little bit here. We said that this is pounds per inch. We said that this was inch, and this is inch. So pair of inches cancel. Pounds multiplied by inches, inch pounds. All right, but I wrote it out because again, it looks like subtraction if I don't. All right, so we could do it that way. We could have converted it over into feet and got an answer in foot-pounds. That's a matter of preference, though.